Hello, everyone, and welcome to PyData Global. We're excited to have you join us for our next presentation. Feel free to use the chat to connect with fellow attendees and share your thoughts during the session. If you have any questions, please post them in the Q&A tab, and we'll address them at the right point in the presentation. But now it's my pleasure to introduce Mark Moyou. He'll be presenting his talk, Understanding the End-to-End LLM Training and Inference Pipeline. Mark is a senior data scientist at NVIDIA, podcast host, and conference director. And in fact, I first met Mark working on PyData Miami back in 2019. So it is my very much pleasure to introduce Mark, and let's give him a warm welcome. Oop. Mark, we might be, actually, I don't know if we can hear you right now. Oh. Can you say something?
What about now? Can you hear me?
Yes, much better. All right, Mark, that sounds great.
We gotta switch mics then. Okay. Good morning or good evening, wherever you are. Great to meet all of you. So today I wanted to give you this intuition about more the inference side, and we'll touch a bit on the training side. And it's just meant to be a very accessible talk for you to understand how these models work, in both in production and just for your own intuition overall. 1 second. Go. So I wanted to just jump into what are some common large language model terms and definitions. So there's the term large language model, then there's small language models. There are many different ways that you can sort of go about understanding this type of material. But first, let's start with what is inference. And if you think of it very simply, it's just getting the output of some particular model. Inference is not relegated to only GenAI. Inference occurs across any type of model. So any model that gives you an output, you're essentially doing some type of inference. And the thing to call out here is I put in multiple modalities. So I put in a small cat, and it comes out as a tiger. I put in a sound wave, it comes out as another sound wave. And that's just to represent where these models are going in terms of passing in different types of data and getting out other types of data. And what's also interesting is that depending on the modality going in, you don't necessarily have to get the same modality coming out. So that, for instance, vision language models will take a bunch of images and give you text out to try to understand what's happening in the text. So as you look at different models moving forward, especially in your career, you want to keep this mindset about how inference is working. But focusing on large language models, I wanted to define, let's look at what a token is. So when you think of a token, think of it as a base unit of a vocabulary or its base unit of understanding. So if someone speaks English, a word is typically a base unit. And then our language consists of a sequence of words, and that's how we communicate with each other. LLMs have a similar mechanism, but their quote unquote word is not an exact, for instance, English human relatable word. Next is this thing called attention. Attention is just an algorithm that operates on a sequence of words or a sequence of data, typically. And that's the main algorithm that's used to say, for instance, what word should I focus on when I am predicting what the final word is. And this is sort of the true innovation behind a lot of large language model knowledge, essentially. Next is vocabulary. This is just all of the tokens that it takes to represent your body of knowledge. So if you take a step back, there are language models that can do coding, that can speak multiple languages and things like that. So imagine what is the total vocabulary that that model needs to encapsulate in order to give you a particular type of response. And next, if you do spend any time with LLMs on a slightly deeper level, you'll hear this thing called KV cache. And the way that you think about KV cache, think of this as all of the tokens that have been processed so far. So it's almost like an LLM's memory, and it's used in order to predict the next token very quickly. So we're going to look at what that looks like coming up. And as you go about building large language model applications and systems, managing this thing called the KV cache. So every time I talk to an LLM, I want that conversation somehow saved. And the next time that I come back to that conversation, I want to be able to, it quickly load that context and get going based on the conversation that we had. Just as if you saw your friend yesterday and you saw him today or her today, you want that conversation to be immediately retrievable. So when it comes to using GPUs, or it comes to speed of response, and it comes to the amount of compute that you need to run these things, there's lots of innovations on the numerical precision side. So a lot of large language models are just a bunch of numbers, and it's just a bunch of math, and we'll actually dive into that a bit more. But one of the innovations is representing each of those numbers where math happens in different precisions. So typically integer math is less precise than floating point math. And what you see here are the different precisions that you can see in different parts of the model. And that's what people use to both compress the amount of memory that's being used, in addition the speed. So typically smaller data in memory processes a lot faster. The math on that is a lot faster. Moving it is a lot faster. So if you look, so int4, so a bit is 0, 1, that's the smallest sort of unit. A byte is 8 bits. So int4 is half a bit, and that represents a certain range of integer numbers. Int8 is 1 byte. FP4 is half a byte in this case. FP8 is 1 byte as well. FP16 is 2 bytes. So a majority of models, when you download them, they're in that 2 byte format. And we'll go into exactly what it means to size different types of models. FP32, this would be 4 bytes, so 8 times 4. And then FP64 is 8 bytes. Folks, for instance, who do maybe a lot of high frequency trading, they need a ton of accuracy. And in most cases, you don't necessarily need that much accuracy to predict the next token. So hopefully that makes sense. When someone says about the context length of a model, that's actually the total number of tokens that come in and the total number of tokens that are going out at a particular period of time. So think of this as the total amount of information this thing can process at once. Just like yourself, if you're talking to someone and someone spoke to you for 10 minutes, you have to remember everything and then you go respond. And that's the total amount of cognitive load you can handle. Quantization refers to, touches a bit of numerical precision, where the entire goal is to try to reduce memory usage so that you increase the speed of inference or increase the speed of response. And this is where you take different parts of the model and you try to represent it in a lower precision, but also keep the same amount of accuracy. So if I can do floating point math, for instance, in FP8 for the same, so in this case, I'll do more accurate math with FP8, but use the same memory as an integer. So you're sort of getting, a lot of benefit there. And then an inference engine, anytime someone says that, just think of that's the optimized version of a model on a particular GPU. So when you go to get high performance of these types of models, you want them compiled on a specific GPU, and that's what gives you a lot of benefit. So let's jump into understanding this workflow of LLM inference. So here I'm saying I have a prompt coming in, write me a presentation on LLM inference optimization. So when I ask that prompt, I actually put that prompt on the GPU. So now it's stored on the GPU. And what I'm showing here on the right-hand side, these are timestamps, timestamp 1 through 4. And I generate the token LLM first. And then I put that token LLM back onto the GPU. And then it decides, okay, what's the next token I should generate? And then it's inference. So that's my second token. Then I put that back on the GPU. My third is. And then the last one is hard. And this happens very, very quickly because it's running on GPUs. So the thing to keep in mind here is that this is what I was saying about context length. It's both the input and then all of the outputs that get aggregated. So there's this constant loop of tokens coming back onto the GPU. And if you think about it from a simple perspective, we speak like that. Every word that I'm saying to you in this presentation, I have to keep track of in order to keep a coherent conversation or presentation going. So if you want to understand sort of the main buckets that happen when a prompt comes in, first, when the prompt comes in, I need to take that text and convert it into some tokens that the model understands. Remember, token is just a unit of that LLM's vocabulary. Once I get onto the GPU, there's this initial prompt processing phase. I need to understand what you asked. If you ask me 10 pages to process 10 pages of documents, that takes me longer than asking me a very simple question. And from there, in terms of what occupies memory on the GPU, it's the awaits, and then all of the other tokens that across all the different people as users. And then I go to generate all the tokens once I understood what you asked. And these are typically numbers that are coming out. So I need to convert those numbers back to the actual words that someone sees at the end. If you want the more technical definitions, so first you have tokenization. So I go from text to the LLM's tokens. Prefill is where the attention mechanism occurs. We'll look at that very briefly. And then once I start decoding, I generate one token at a time. So that's denoted by these individual bars here. And just remember, all of this is cached on the GPU. And then I detokenize essentially back to the corresponding language. It could be English, it could be Spanish, it could be code in this case, depending on what it is that you've asked. If you want to get a little deeper into what prefill is and the attention mechanism and how some optimizations that happen when a lot of different people are hitting the system, I highly encourage you to read this paper, because when you think about these systems interacting, it's just not you using the system. It's multiple people using the system. And think of yourself as the system. And if multiple people came to you with requests and they're asking you a question, you have to kind of sometimes maybe wait to process this question, but these optimizations will help you to process all of those requests coming in at once. And now I want to give you the intuition of how text data turns into some type of tokens or some vector representations. GPUs are very good at doing matrix math, so we're going to see how that works. So I'm giving you a proxy here where I'm going to convert every 4 characters that I see. I'm going to use that as a proxy for what a token could be. So that means it's not necessarily an entire word. In some cases, it is a word, so we'll also see that as well. And I have 2 arrays. One is showing the actual token. So this is the text itself that will be stored. This is just a simple example. And then I have a corresponding index because you don't want to move all of that text around. You can just pass a number, and that represents that piece of text. So my job is to convert that input text through this tokenization process into a vector of token IDs. And that's what the model is really going to see. So if you look here, I'm going to say, make me sound smart. I go through tokenization. I get the corresponding token IDs. In this case, there's a one-to-one relationship between the words and the tokens that I've showed, but that's not always the case, as we'll see coming up. So when you want to understand what vocabulary a particular model has, so I'm showing a Llama 3.18b instruct. If you go to Hugging Face and you sign up, you can get access to see these model files. So this is what models actually look like to a degree, at least the files themselves. And then this tokenizer.json, I scrolled a bit down. So if you look at it, there's a bunch of different tokens that it's assigning. But it's assigning, for this symbol, I'm going to assign the index 0. For this symbol, I'm going to assign the index 1, etc., etc. So anytime a new piece of text comes in, it's going to chop up that piece of text and find out which of these building blocks are remaking that particular piece of text. And as you can see on the right-hand side, in this case, Llama 3.18b has 128,000, and we'll see that later on as well. So you can see the corresponding numeric index for the different words, but we have WH, type is a word because it apparently occurs very often. And the way that they develop these tokenizers is the entire training data set. They try to find what is the smallest set of subwords that can re-represent that entire training data set. In addition, the new text that's going to come into the system can it also potentially represent that as well. So now that I have each of these tokens, each of them has a corresponding token ID, each of them has an embedding vector. So inside of these LLMs, during the training process, I essentially set these as parameters. So these are all parameters. And then I learn an embedding vector for each of these tokens based on all of the training data that I used. So my goal is to now get to this representation of an embedding vector. So why are these embedding vectors important? The main intuition I want you to have, I'm just showing a simple 3D example. So X, Y, and Z coordinates. So that has 3 different values. So you have 3 different numbers. That's just an embedding. That embedding is actually a coordinate. And now that I have 2 vectors, I can compare those 2 vectors typically through some vector space distance, depending on how the model is trained. And if we look on the right-hand side, this is the config.json file from the Llama 3.18b. And this is actually going to give you, if you look at this hidden size, this is saying, okay, this vector that represents that token is 4,096 dimensions. So think of X, Y, Z, and whatever other letters up to 4,096. And that's the hyperspace that exists for all of these tokens to relate to each other. So when your prompt comes in, it gets converted to tokens and embedded in this high dimensional space. And you can see the total number of vocabulary terms in the model itself. So coming back to this, if I say make me sound smart, I'm going to tokenize that, and then I get this sequence of vector token IDs. I fetch the corresponding embeddings. Those embeddings allow me now to do a bunch of relation between words, math, and a ton of stuff. And I put make me sound smarter just to show that the subwords are not typically an entire human word. So now what you've done is when you prompt an LLM, what you're really doing is creating a matrix on the GPU. The larger that particular prompt, the bigger the matrix. What a GPU is really great at, they're great at processing matrices. So this is why most folks need GPUs in order to run some of these large language models. Next, I want you to understand how these tokens are processed once they come into the actual LLM itself. So the first is the attention mechanism, intuition I want you to have. It's a fantastic topic to go educate yourself on, is this notion of how do I focus on what is important in the text? If you gave me, I don't know, 120,000 words, which of those words are important to answer the question and also to predict the next token? So it's always about predicting the next token. So I have this prompt coming in. I'm saying, just make me sound smart. I'm going to predict this thing called LLM. I've embedded this particular set of text. So now for each word or each token, I have the corresponding embedding vector, which makes a matrix. The model weights are basically a bunch of matrices. So we're just doing a bunch of matrix math or vector matrix math in certain cases. So when I do this matrix multiplication, what's really happening intuitively, when you do this matrix multiplication, I am projecting these vectors into the space of, whatever space that model understands. And this is the corresponding representation of what it looks like. It's just a bunch of new vectors. And this is what the LLM uses to then, I didn't put the details of the attention mechanism too much, but it does a bunch more math to figure out, okay, for this token, how many of these other tokens relate to it? And now I form a new representation of that token. So there's this thing called query key and value. This is where query is sort of the way that a token can go relate to all the other tokens. So it'll go query times all of the keys. So find that similarity there. And then you sort of reformulate with this value matrix. But the main thing to take away from this is that this is how inference gets done very quickly. So now this is sort of the LLM's memory where I keep tokens that first came in. So the next time when I generated this token LLM, now I have to put that token back onto the GPU in order to generate the next token. So notice I don't pass in the vectors that I initially had anymore. They're stored on the GPU. And now I just embed this new token that just came in. I just generated that token. It comes onto the GPU. I do the same. Now we're doing vector matrix math. And now I can compare this new key vector with all of these vectors that were stored on the GPU before. And this is how that inference speed increases. And that's what your KV cache is really called, right? All of the tokens that were put onto the GPU. And once they've gone through this matrix multiplication with the model, they're now essentially interpreted. So these LLMs have multiple of these particular models. So Llama 3 has 32 attention heads, and there are more matrices, but this is a view of what it looks like. So a good proxy for you to keep in your mind, anytime you want to know the amount of memory that an LLM picks up on a GPU, take the number of parameters, multiply it by 2, and that's your size in FP16 memory. So FP16, so 8 billion times 2 is 16 gigabytes of FP16 memory on the GPU. If you use an FP8, right, which is half of FP16, it's actually 8 gigs. So I get another 8 gigs that I can host tokens with. When you work with these models, you'll see this thing called safe tensors. It's essentially just a very efficient format for hosting tensors or matrices, or multidimensional matrices in some cases. And it's just faster than loading pickle files. So I showed the model safe tensors index.json. So if you go look at this on Hugging Face, you can see this yourself. And you can see this is what an LLM looks like. My total parameter size. So this is actually 16 gigs. This is number of bytes. So when you put this in a calculator, it's 16 gigabytes. And I just call out the key, query, and value matrices that you kind of got a view of before. So these are just a bunch of matrices that I'm loading. So it's a bunch of matrix math. So hopefully you have that intuition. I recommend you check out this blog on inference optimization. And now just wanted to put a couple of things on model training. So when folks go to train these models, there's this phase called pre-training. This is where I take a ton of text data, and then I essentially learn to predict the next token. And so it's a sort of an unsupervised learning problem to a degree, but this just has general understanding of how to predict the next token given a sequence of tokens coming in. So supervised fine-tuning is where I now go to try to update this particular model for a specific task. So I'm going to update all the parameters of that model given some input and output labeled training data set. Where most folks are using today, updating all the parameters, that's fairly computationally expensive. So what you want to do sometimes is to make it more efficient. So they'll train a smaller adapter model, which is called a LoRa. We'll look at that coming up. So you could still use the knowledge of the base model and get some knowledge. Think of it like the matrix. When you upload a new module in your brain, you take all your base knowledge. I upload how to ride a motorcycle, I can go. And then instruction fine-tuning, when you speak to these systems, they have a personality. They respond to you in a certain way. They do certain things. So the process of getting a model to do this is called instruction fine-tuning. I didn't mention things you might hear, reinforcement learning with human feedback. That just allows the model to really fine-tune exactly how it responds. So it'll have multiple different variations of the same answer, and that model will predict exactly what's happening. And from there, let me just make sure time check. Yeah, so we're gonna go a little faster. So low rank adapters, highly recommend you check out this paper. So I have my pre-trained weights, and essentially I'm going to represent this entire matrix as a composition of two smaller matrices, and that's the module that I'm going to train. So I'm going to train with these two smaller matrices. So it's almost like both of them are making a decision, and the smaller two matrices are learning how to make that decision given some new data. And from there, there's this thing called a rank. That's just the size of that matrix, typically less than the total number of rows or columns of the original matrix. So that's why it's smaller. And what it looks like from a deployment perspective, if I have 5 different use cases, and I didn't have a LoRa, I'll have 5 different models, let's say on 5 different GPUs. But in this case, I can have 5 different LoRas, a single base model, and host that technically, all on a single GPU. So there's an efficiency that you get from doing this type of training. Jumping into metrics, I think we're getting a little closer. So if you are doing any performance measurements of LLMs, I recommend you check out this open source package called GenAI Perf. It's part of the Triton open source Triton. It's an inference server from NVIDIA. So people measure this thing called time to first token. So when you send in a prompt, how long does it take me to get back the first token? And that's a measure of understanding, essentially. Next, there's lots of things on the slide, but inter-token latency. So when I start generating tokens, I want the space between those tokens, the timing to be fairly consistent, especially as the sequence grows. So that gives me a good view as to how efficient my generation is. And lastly is this time to generation. How long did it take me to first get your prompt and then completely finish it on the other side? And to round out, I wanted to expose you to some packages from NVIDIA if you are doing large language model inference. So TensorRT LLM is an open source library that you can leverage. So essentially what it does, it will rewrite these models in an optimized format on NVIDIA GPUs. And essentially you get a ton more performance benefit, especially when you do things like FP8. You have the ability to sort of extend the package. So if you can do a bunch of custom things with your own models, and then that particular model, which is, think of it as a optimized format, it's a new file format, it gets hosted on Triton, and Triton will manage all of the requests that come in. So you could do a bunch of scaling. You'll hear something like in-flight batching. So when my request finishes, someone else can get into the system. They don't have to wait for everyone's request to finish. Here's an intuition of what inference engines look like. So essentially, I'm trying to compress that, make a smaller, more accurate, just as accurate version, but just to increase the speed. This is kind of where inference is going, FP16 to FP8 to FP4. So smaller memory sizes, faster speed, same accuracy. If you're looking at GPUs where this thing works, I encourage you to use any of these GPUs up here. They give you sometimes access to FP8. These two do as well. Ampere does not give you access to FP8. Check out this particular blog if you want to learn more about speeding up inference. And if you want free GPUs, go to build.nvidia.com, sign up for a free developer account. You get 1,000 inference requests for free, and you could test a bunch of different open source models on there. And feel free to connect with me on LinkedIn, and I'll answer any questions, which I don't necessarily see any in the chat.
Yeah, please, if anyone has a question, we have about 2 minutes remaining, so please post them there. But in the meantime, we'll wait to see if anyone has any questions. But Mark, we appreciate you. Oh, looks like we got one.
I see someone. So someone asked, will you be able to briefly describe how multi-head attention mechanism promotes parallelism and thus improvement in compute performance? So if you go back to that slide where I had a bunch of different attention heads sort of allocated. So when a prompt comes in, we're going to essentially convert that into a matrix like we saw before, and then that matrix is just going to get distributed and multiplied against all of these other types of matrices. So it really comes down sometimes to the GPU, because different GPUs will have different configurations of memory and number of cores that they can sort of split this type of math. There's actually a lot of, it's not an easy problem to solve, especially when the matrices are not sometimes skinny or they're wide. It depends on the size of the models. But the GPUs will be able to compute all of those attention heads at once, and then collect all of that data, especially when you think about scale. Sometimes these models exist across multiple GPUs. So there's communication, a lot of communication that has to happen. This is why networking is really important for some of these industrial systems. So hopefully that makes sense.
Hey, Mark, there's a lot of interest in a link to your slides. Is that something you can post real quick?
I can, yeah. How? Let me see.
We can do it in the chat real quick so people can grab the link right before we wrap up.
Will this chat persist, or can I email that to you? I don't think I have a link directly. I'll link. I gotta figure that out. Connect with me on LinkedIn, and I'll message it to you. That'll be the easiest. And just put in the message PyData, and I'll make sure that I have the context. I'll be able to send it to you.
Okay. Well, thanks, Mark. That's great. We are at time, so it's a good place to wrap up. But thanks for joining us and for presenting, and looking forward to seeing everyone later. Take care.
See ya. Bye.